Hello, greetings, welcome, and let's take a look at exercise 5.2, which is our chapter 5 homework problem. So now in chapter 5, we introduced the concept of functions, then also the strategy of encapsulation in terms of writing our functions. Now in chapter 5, we haven't discussed vectorizing our functions and having multiple functions in a file. That's going to come about in the next chapter, in chapter 6. So for exercise 5.2, we're asked to build upon our friction factor code that we've worked on for several chapters now. And so we start out, this is just a recap of the expressions that we've been working with. And for part A, we're asked to write a function that takes as an input my Reynolds number and relative roughness, and then returns the friction factor. And we're given two different test cases that we can use to test to make sure our code's working correctly. And so what I've done, so I flip over to MATLAB, is I've downloaded our M file. So this is our M file from chapter 2, and then this one is our M file from chapter 4, I believe. Okay, and so thinking of the first problem, I'm going back to chapter 2, because again, in chapter 2 we wrote a script that has a precondition of Reynolds and relative roughness and returns friction factor. And so what we're going to do is I'm going to start by opening that script. Okay. And part of the motivation for encapsulation is, let me move my head, right? So we know our file's saved over here. So part of this encapsulation process is write the script. And when I write a script, scripts can be easier to troubleshoot and debug. Why? Because the script's going to operate from my base workspace, so I can use that to check intermediate calculations and things of that nature. And so once I'm sure that it's working, then I can encapsulate it within a function. And so if I look back at our script here, right, we had a precondition of Reynolds number and relative roughness, so that was defined in our command window, and then it returned the friction factor. And so how I'm going to go about this process of encapsulation, and sorry man, my head is just getting in the way, right? So I wanted to make my screen bigger so I could see everything. Okay, is I'm going to start, okay, by keeping this as is. So if I don't suppress F, okay, I'm going to come back here and I'm going to test my code. So we're told for a Reynolds number of 1e to the 5. So if I have a Reynolds number of 1e to the 5 and a relative roughness of 1 over 30, okay, which my precondition is, I call that 1 divided by 30. So then if I call my script friction factor, okay, cool, I get my 0.601. Great. Okay, so that checks out. Okay, so what I'm going to do next is I'm going to clear F, right? Well, let me just do clear all, okay, just to make sure I'm set. Okay, and so what I'm going to do next is I'm going to take my function. Okay, I'm going to use my generic res, right? And res is equal to, I'm going to call this friction factor. I want the name of my function to match the name of my file, right? This is my function file, and this is my top function. Okay, and my friction factor, so I don't have to modify my inputs, so I don't have to modify my code at all, are just going to be Reynolds number and relative roughness ED. So for my output variable, I use res, right? I could just as well use F. It's just a habit that I have, so that when I get to my end statement, whatever I want to return, I'll make sure it's stored to that variable ED. Okay. So what I'm doing now is I'm just highlighting everything and then tabbing it in. Okay. Tabbing it in so that now as I go to a new final line and add my end statement, right, it's clear, right, in terms of what's included within my function. Res is currently highlighted. Res is highlighted because I'm not actually assigning anything to res or returning anything. So I'm going to add a line, assign F to res and return. Okay, and so I'm just going to assign to res F. Okay. I'm going to come up here to 22, suppress that output since it's no longer needed. and then I'm just going to have to touch up my documentation. Okay, and so this will pretty much be my exact documentation. So again, at the beginning of my documentation, I like to start by copying my function signature so that I know exactly how it works. Whether or not you include the function or not, right, I'll leave that up to you. So I'm going to copy my signature, and then I'm going to add my comment. So just like script, right, now this is a function to compute the friction factor. Now it's a function to compute the friction factor for given Reynolds number and relative roughness. Okay, and that's pretty much it. Okay. And so maybe I'll add a note that RE is Reynolds number and ED is relative roughness. Okay. Alright, so I'm going to save it. Okay. And so now I need to update my call when I come down here to the command window. My given friction factor, so let me call it F. Okay. And actually, let me kind of make this a little more formal. Okay, and so this function's saved. So let me run it once from the command window. Then let me make it a little more formal. So how I would run this now is F is just going to be equal to. Let's say F is equal to friction factor. Okay, then need an input of Reynolds. The one base case we're given is 1e to the 5. And then we had a relative roughness of 1 over 30. Okay, so looking over here, right, note in my base workspace, I don't currently have any variables defined. Okay, and so remember what's special about a function is a function has its own workspace. So in my call here, okay, I can suppress the output or not. Okay, I'm passing information to the workspace of my function. So this first argument here within my function will be assigned to the variable RE. The second term 1 over 30 will be assigned to the second variable ED. And then whatever is returned back from the function to my base workspace, where I'm operating here in my command window, I'm going to assign that to variable F here. So all of these intermediate variables within my function, all right, are only going to exist within my function and will be essentially cleared or deleted once that function exits. Okay. So cool, right? I just created this friction factor code that now I can run. And part of the idea or motivation behind this function is that essentially I've just created this black box, just like sine and cosine and all the other built-in functions in MATLAB. Now I've got this black box, and then I can pass to it Reynolds and relative roughness, and I know that it's going to return back friction factor. This can also be advantageous in terms of simplifying larger pieces of code where, okay, this makes sense to me. This is computing the fanning friction factor. I don't need to know the details of how it's done, but I know that's what it does, and so it can actually help streamline then my code as well. And so how I would generally use this then is this is good. But what I might do is I might create a new script, okay, and maybe this script I'll call chapter 5a. Or maybe chapter 5 homework. Okay, and so I could use this in that script to test solutions to the chapter 5. I've got to move my head again to the chapter 5 homework. And so we'll start with part A, right? So I can kind of document my work, if you will. And so for part A, I'm going to look at the two known cases given. And so the first was we had a Reynolds. So we had a Reynolds of 1e to the 5. And then ED was 1 divided by 30. Okay, and so if I do that, I'll call it, say, F1, my first friction factor. Right, now I can call my function. Right, and so I can call my friction factor. Right, and notice even over here, okay, this is a function file. Right, so even the symbol is different than a script. So I'll call friction factor, and I'll just explicitly put in Reynolds and ED. Okay. I could define them as well. Okay. and I'll display that. And then the second case, I'll look at Reynolds of, where are you? Reynolds still of 1e to the 5, and then this relative roughness. Reynolds is 1e to the 5, and then ED is equal to 1 divided by 1014. Okay, bam. Okay, and if I do that, I can have F2 is equal to friction factor 1 and maybe, hey, what I can do now is just do Reynolds is equal to 1e to the 5. Maybe I even make it even simpler. And then 1 divided by 1014. Cool. So I save it. Now I can run it. Okay. Now with my one requirement though is within the script. Right now I can call this function. Right, and I know this is just some black box that's going to return the friction factor when I pass to it Reynolds and relative roughness. The one thing that you do need to make sure though is that your script and your function are in the same directory. Okay, that way your script can see your function. It needs to be in the same directory or in your MATLAB path. We haven't messed around with the MATLAB path, so just remember it needs to be in the same directory. Okay. And I get 0.601 and 0.207. Okay, bam, those are the two values we're given. Okay, great. Okay, so that's part A. Got it. Life is good. And now I have this code that no matter what I want to compute in terms of friction factor, right? I know it'll work. Now part B. Okay, part B we could tackle in a couple different ways. But part B says, next, use your function to plot F versus Reynolds for a given relative roughness. That is, make your own Moody chart. Cool. For the purpose of this question, write a script or function where you loop over Reynolds values over the range 1e to the 3 to 1e to the 5. And for each Reynolds, use your function to compute F for the case of ED, a relative roughness of 0.1 and 0.001, and then plot. And so yeah, we're told we can use log axes and all these different ways in which we can fancy it up. Okay. Now I'm going to kind of tackle this two ways. Okay. The first way is, again, part of writing this function is now I just have this black box. And I know that if I pass to it a Reynolds number, a relative roughness, it's going to return the friction factor. So it can help in terms of simplifying my code. Okay. And so I'm just going to roll with that for this first case. Okay. And so let me make this bigger. Okay. And again, I'm just thinking of, I've got this black box, this function that can compute the friction factor. I'm going to try and use that. The other case we'll look at is we can look at encapsulating our code from chapter 4, but let me start with this case. And so first we're told Reynolds numbers from 1e to the 3 to 1e to the 5. Okay, so I'm going to call this part B. Okay, part B. And so I'm going to loop over Reynolds from 1e to the 3 to 1e to the 5, looking at two different cases for ED and plotting. Okay, and in this case we're told to use a for loop. What'll be much better is we'll vectorize the code in chapter 6, but for now let's just work with this. Okay, so kind of like when we tackled this in chapter 3, was it? Let me just start by creating the vector of Reynolds numbers. So Reynolds number, I'll do linspace 1e to the 3, comma 1e to the 5, and I'll start with that generic 100 data points, or default 100 data points. We're going to look at two cases of relative roughness. ED1 is 0.1. Okay. The second case is 0.001. two different cases of relative roughness. Okay, great. Now, since I'm using for loops, I'm going to create vectors to store the friction factor. And so I'll call this F1 is going to be equal to zeros. And then I can do size of Reynolds, or I can do 1 comma length of Reynolds. So I want one row, and then however many columns I have for Reynolds. Okay, I could type in 100, but this way, if I change this to 1000, I don't also need to update the variable here. Okay, so F2, make zeros, 1 comma length of Reynolds as well. Bam. Okay, and now I'm going to loop. All right, and so now my loop will look like for I is equal to 1, then length of Reynolds. Okay, and what am I going to do each iteration? Well, F1I will just be equal to, I'll call friction factor. First argument is Reynolds, so that's going to be REI. And the second element's my relative roughness, which in this case is ED1. Okay, cool. I do the same, trying to copy and paste, I do the same thing for F2. And then this has to be ED2. So this is looping and computing. Okay. Then once I have that, it's just a matter of plotting. Now, whether or not I want to put them both on the same figure or not is up to you. Okay, but it'll look like something like figure 1. Oops, sorry. I was trying to add spaces so I can see the bottom of my screen. Okay, so the first case might be my independent variable is Reynolds, so it's Reynolds versus friction factor 1. And I'm going to plot this as I'll just do black, and I'll plot it as a black line. Okay, I need to make sure I have a hold on. So I'll start by actually clearing the figure in case anything's currently plotted. I'll have a hold on. I'll just use a generic plot for now, and then we can see what it looks like to update it. And the second one I'll make red. Okay, my X label is, I need to use double quotes so I can put a parenthesis on Reynolds number. My Y label is my friction factor. And then I'll add a legend. So ED is equal to 0.1, and ED is equal to 0.001. Okay, bammo. And that should do it. So if and I said let's just do grid on just for fun. So we'll do the normal case, and then we'll see what log looks like. Okay, so all I did is I've got this black box, this friction factor code working now. And so all I'm going to do is I create a vector of Reynolds numbers, store my two relative roughnesses to variables, and then I'm just looping over my Reynolds numbers in computing. Okay. All right, so this code is much simpler than what we had before. And then again, I have this black box. I know that in goes Reynolds, out comes in goes Reynolds and relative roughness, out comes friction factor. So I'm not worried about the details. So if I were to run this, so it's a script, I can just click the run button. It'll perform our calculation for case 1 as well. Oh, 'tis madness! I've got a line. Something's not shaking up right, but that's okay. We've got this. All right, because I know it worked for the base case, and so it ought to work here. Okay, and so the one thing I'm going to do, let's see, I have Reynolds versus my two friction factors. I have my hold on. Okay, let's make this log, okay, as we were instructed. And then once it's working, I'm going to make this 1,000 data points and see if that helps. And let's see. Oh, 'tis madness. Something's not looking right. So let's see. So what I'm going to do is I'm going to start by just plotting one of these. Okay, so I'm going to just plot one and make sure it's looking right or looks right. And it doesn't. Something's not shaking out. But okay. So, friction factor takes in his Reynolds and relative roughness. So this is the ith element of my Reynolds vector. Put in the ith element of this F1 vector. So that should be fine. My range is okay. Reynolds are 1e to the 3 to 1e to the 5. And ED is 0.1 and 0.001. Okay, so that should be okay. So let me comment out the legend. Let me plot case 1, or case 2. Again, let's just do plain plot and make sure it's working. Not quite. Something fishy is going on. 1e to the 3 to 1e to the 5. Arc. Okay. It should work. I'm going to crank up the number of data points and make sure that's a red line. So it doesn't look right. Okay. And if I look here, so I have F1. Okay. It's of length 10,000. Oh, and I'm guessing it's how I'm writing, right? And it's all zeros. Okay. So something's not right. So here my for loop is messed up. This is for I equals 1 colon length RE. Okay, bam. Okay, so I'm going to calm this down. I don't want to do 10,000. I'm going to do 100 now. Make sure it works again. Okay. Let me try and plot both of these and add my legend. Okay, so my loop wasn't set up correctly. I didn't have my lower bound for my loop index. Okay. Now I run it. So now that looks right, right? So now this looks beautiful. Okay. I could click on that and move it if I wanted to. Okay, if I wanted to add more data points, I could. Right? It's just proceed with caution. So if I make 1,000 data points, as I add more data points, the more and more computationally expensive it's going to get. Yeah, it'll be smoother, but okay. And so there it is. And then if I want to try log, that'll look like this. Okay, so that's log. That doesn't look like log. Why doesn't it look like log? So let me try. Does the position of hold on mess it? Yeah, so it looks like hold on can't come initially, because if hold on comes initially after CLF, then it's linear axes that don't modify it. So crazy. So when I type hold on after CLF, it uses linear axes and then log log doesn't work as you'd expect it to. Right, so now these are log axes, right? I can tell by the uneven spaced tick marks, right, on both my y and x axis. Okay, yeah, so that's a log log plot. You can make it bigger if you wanted to. You can make it smaller if you wanted to. Right, so now that I have this running, I can go from a tiny Reynolds number. All right, let's go from 200 up to 1,000, and then I'm going to call it quits after that because my battery is about to run low. All right, so I can increase the range and play around. But I'm going to stop here. The other solution we could have had was taking our code from chapter 3 and encapsulating that. And I'll do that in another recording so that it doesn't get too long. So I'm going to save this and upload it so that you have this as a reference. But again, my strategy was I create this function, this black box, and then once I have that, I can just use it as in my code. Hope that helps.